So good morning, everybody. Welcome to the morning session of the first talk. So this is the last talk of Professor Marius Tucsnak. So yes, please.
Thank you very much. And thank you for being still here, even after 3 lectures. Today I will discuss a slightly different topic, which is time optimal control problems. So to have, of course, I would say a general view of control theory, controllability and observability are just, in fact, globally speaking, very small parts of control theory for linear system, but which interest a lot of mathematicians. So they focus, especially PDE people, focus on this because probably the most challenging mathematical questions are there, and they can also be formulated in a simple manner. So formulated in a simple manner, but the solutions often are quite complicated. Of course, if we refer to finite dimensional linear system theory, much more important problems will be stabilization, from the application viewpoint, I would mean, and optimal control. Among the optimal control problems, one which again attracts mathematicians because it raises nice challenges is the time optimal control. I will so try to describe some, let's say, by now classical and some new results which are relevant for this topic in a as self-contained manner as possible. So to begin with, the general aim is to steer a given system. What a system is, I define in a very axiomatic way, from an initial state Z0 to a target state Z1 by imposing restrictions on the control. Typically, the norm of the control should be bounded almost everywhere in time, or you can ask the control to lie in a certain polyhedron if you have a multiple input system. And with this constraint, we don't impose constraints on the state, at least at this stage. With this constraint, we want to do this job as quickly as possible. So when you look to this question, first you would like to know, is it possible even with L2 controls to go from Z0 to Z1? Because when I say this, it's clear that my control should be, in fact, L infinity in time, otherwise my restriction doesn't really make sense. So then I should ask myself, can I reach the target with controls which are in L infinity and with a norm smaller than 1? Is not the same thing. It might be, there are examples of systems where the first property is true, but the second one is false. Then, once we know, or sometimes we just assume that it is possible. We don't need to know by advance. Sometimes we just assume that it is possible. We are asking ourselves, is there exists the time optimal control? And what fascinates mathematicians, and it's pretty important from the practical viewpoint, is to know that if the control is bang-bang. In other words, is it all the time saturated? Because of course, intuitively, if you want to do the job as quickly as possible, you should be all the time put all your energy in the system. And of course, then there are the computational aspects which I will not address. Let's say almost high school example is a rocket engine. So you have a kind of rocket on a track, so you can something on wheels. You neglect friction, and you write Newton's law. Z double dot, Z is the abscissa of the, let's say, the mass center of my rocket engine. And the equation of motion is Z double dot is equal to U, where U is the force by which I act on the body. And I want to go from initial position Z0 to a final position Z1. So I leave from rest at rest from Z0, and I want to arrive at rest in Z1, but with a force which is constrained to lie between -1 and 1. I don't have an infinite amount of power. So here the solution is not such an easy problem. If you try to solve it by hand, it is possible, but really it requires some work. And the solution is to apply a maximal acceleration up to the middle of the distance between Z0 and Z1, and then maximal braking, which is very uncomfortable, but that's the optimal solution, the solution which which allows you to reach the target in an optimal time. So the problem is, there is a very important literature on these problems for finite dimensional linear systems. So it's one of the important subjects in finite dimensional system theory. A first PDE example, which I will come back at, let me take a heat equation. So I have a room, I have a radiator here, and I want to achieve a temperature profile as quickly as possible with controls which are again a constraint. Here I can ask a constraint in T and X. We'll see that generally when I want so U of T and X, I ask him almost everywhere to be smaller than 1, both in T and X. Sometimes we are not able to do that, but in this case, we will be able to solve the problem with this constraint. Here again, the solution which we will obtain will be always either 1 or -1. It will switch between 1 and -1. But this, to prove this, you will see this is much more complicated. Let me remind again the notational framework with X the state space, U the input space, the semigroup, the admissible control operator for the semigroup T. So this is a framework I have developed very widely in the previous lectures. With this framework, when I look to the differential equation Z dot is equal to AZ plus BU, so this is my system, I can write the solution as the semigroup applied to the initial data plus the input map phi T applied to U. We have the notion of exact controllability and with its dual exact observability, and the notion of approximate controllability with its dual approximate observability. What is C1D? C1D is just it's V star T star of phi. That's for phi in D of A star, but C1D, if my pair is admissible, C1D can be extended to a linear unbounded operator from X to L2 of 0 tau capital Y, which I cannot evaluate using this formula. It's extension by density. This is in general, if B is unbounded. So that's the classical, some of the classical dualities. We'll see others. So in particular here, I will be interested in states which are reachable by L infinity in time controls. This space, I call it R tau infinity. And of course, I say L infinity exact controllability means that this space is all of X. And this is equivalent, again, by duality to an observability inequality. This is not so obvious, no, because these spaces L1 and L infinity are not reflexive. So you have to do the proof carefully. You cannot just say I apply a duality, even if most of the people do, and in fact they are right, the result is correct finally, but it requires a small proof. Then I have a notion of approximate controllability from E. So here I take E, small e, sometimes I might denote it by capital E, a set with positive measure. And then I define the notion of approximate. I can also define the notion of exact or of null controllability from E, which means that if I take inputs which are active only in E, then I can reach all the states for exact controllability, a dense subspace for approximate controllability, or the range of the semigroup for null controllability. Of course, so this looks like a strange problem, even let's say from the practical viewpoint. Why should I be interested in acting only in a set of positive measures, which is not necessarily an interval? That's the point here. E is not necessarily an interval. From the practical viewpoint, I have strictly no, let's say, no reason to do that. But you will see that this property naturally occurs as a step in the study of time optimal control problems. And of course, again, mathematically it's challenging to say I cannot act on the whole time interval. And in fact, we will see, we can also say I cannot act in an open set in space. I can act only in a set of positive measure when I will really write PDEs. Both of these are important for time optimal control problems. But for practical purposes, they are clearly not so important directly. So how can I state now my problem a bit formally? For the moment, I am in an abstract setting, so I don't say who is capital U. So this is why I put the restriction only for the norm of U of t, norm of U of t in capital U. Yeah? So I put the restriction smaller than 1. So this is my admissible controls. So I assume here, to formulate the problem, I can assume that I can go with such a control from Z0 to Z1. So I have at least one admissible control. And then I want to determine tau star such that I can do this job in minimal time. The first thing being, of course, to prove that such a tau star exists. Clearly, tau star, if Z0 is different of Z1, or it's far enough, cannot be 0. Because I need some energy to go far away. Of course, I would like to which I didn't write here, to write some optimality condition, and as a consequence, possibly, as a possible consequence, to prove that U star is bang, so that the norm of U star is almost all the time equal to 1. In the particular case, U is L2 of something, which is often the case in applications to PDEs, I can write my constraint, the modulus of U of t and x smaller than 1 almost everywhere. And the bang property would be that this is equal to 1 for almost every tx in the product space. So this is, of course, better from the application viewpoint. Some very classical biography in infinite dimensions. So there is a book of Fattorini devoted only to this, where in fact B is almost all the time identity. The book is very beautiful, but with this, let's say, limitation. There are some interesting paper after. A very important reference, which I will come back, but and which is essential for parabolic systems, is the paper of Meitzel and Zeidman, and which has been somehow generalized to to a larger class of parabolic PDEs by Wang and by Gensheng Wang and his co-authors. Here there are several papers, early papers where Gensheng Wang already contributed. And you can find a very good chapter on that in the very classical book of Lyons on optimal control. Really excellent presentation. And again, the book of Fattorini, which in fact previously I quoted papers, so the book, another book of Fattorini. So I will separate the presentation in two parts for which the methods are quite different. First, let's say, roughly speaking, exactly controllable system. I'll make this more precise immediately. If we think to application, it will be of type of the Schrödinger or of the Euler-Bernoulli plate equation. We'll see the applications immediately. So first, the abstract result here, my B is bounded, but in fact the result holds with a bit very slight modifications for B admissible. So here we can, this is not really a limitation. And then I assume that AB is exactly controllable in any time. So here exact controllability means exact controllability in any time, which of course will exclude wave equation with distributed or internal control or boundary control. Then a time optimal control, an optimal time exists, and it is characterized by the a version of Pontriagi's maximum principle. So this is Pontriagi's maximum principle for time optimal control problems, which it says that there exists a non-zero state Z such that at each time t, that's important, U star of t maximizes this inner product. In fact, for time optimal control problems, this optimality condition has been obtained before Pontriagi's maximum principle by Bellman in a quite well-known paper of Bellman for finite dimensional system. But here the situation is very close to finite dimensions, finally. We just have to prove correctly. But if I look to the conclusion, it's the same as in finite dimension. If A and B are matrices, the same holds, but they don't need exact controllability. They don't need controllability as far as I remember. So I have an extra assumption, but otherwise, everything is like in finite dimensions. So here, what does this mean that U star is maximizing this inner product? It means that if this is different of zero, U star has the same direction. If you want to maximize the inner product with a given vector, you should take a vector which has the same direction. So this is why if B star, T star, Z is different from zero everywhere, this optimal control will be nothing else but what I write here. And what means that this is different from zero everywhere? By duality, this is equivalent to the fact that AB is approximately controllable from any set of positive measures. Again, this assumption is not necessary in finite dimension. It's, if I have controllability, this is automatic in finite dimension. Why? Because the observation is analytic in time, time analytic function. Here, my observation has no reason to be such. So this is why I have this assumption, exact controllability in any time, and approximate controllability from any set of positive measure. And then I have existence uniqueness of the time optimal control, and for every initial and final state. So I have also an existence theorem. I don't have to assume, of course, that I can go from Z0 to Z1. I can prove it. So how we prove all this? So in fact, how we prove the maximum principle, because this is the key of this point. So I endow my state space X. In fact, this is the norm of R tau infinity with the notation I introduced in my second lecture. So it's the L infinity norm of the the smallest possible L infinity norm, which drives the initial state 0 to Z in time tau. So this is clearly a norm on X, and it's well defined because I have exact controllability in any time. No? And because I have exact controllability, this norm is equivalent to the norm in X. That's a very important point. Because of exact controllability, this norm is equivalent to the norm in X. Then the remaining part is simple. So this set here, B infinity is tau, so it's the unit body in this space, in the state space, will be a kind of convex open set. No, convex set with non-empty interior. Because I accept it here smaller or equal to 1. And then, so this is in X. So this will be B infinity of tau. How did I write it? B infinity of tau. Now, the first remark is that if I have a time optimal control, the target will be on the boundary of this. So Z1 will be on the boundary of this set, because otherwise I could do it in a shorter time. Imagine it inside. I could do it in a shorter time. And that's important. All what I'm saying is with respect to the topology of X now. And then I just use the geometric version of the Hahn-Banach theorem, which says that for such a set convex with non-empty interior, for every point of the boundary, I have a support plane. No? And then I write this, and I get the maximum principle. That's all. So essentially, this is the proof. The key point being to realize that I have this. Oh no! So in fact, what I say is something I said is completely incorrect. I said that B goes from U to X is not essential bound. It is essential. It is essential. Why? Because so I assume that my system is L2 exact controllable. And if B is bounded, then it is also L infinity null controllable for free. You write the minimal null control L2, it is automatically L infinity. So it is important. So sorry for this mistake. Okay. This is why. So this is capital when I'm saying that these norms are equivalent. Otherwise, with L2, I would have equivalence, of course, even with B unbounded. But I'm not interested in L2. I'm interested in L infinity here. Okay, so this is a proof of this abstract result, so which gives bang-bang for systems which are exactly controllable in any time and approximately controllable from sets of positive measure. First example, Schrödinger equation with internal control. So I take omega, so I take which are the situation when I know that this equation is exactly controllable. Either if I have a rectangular domain and O is any open set, or when omega is arbitrary and O satisfies the geometric optics conditions. So these are the situations where I know almost all the situations where we know that the system is controllable. Then I take an initial and a target state, Z0 and Z1. Then when I'm saying that I'm able, in L2 both, I'm saying that I'm able to find a control which drives me from Z0 to Z1 with norm in L2 of O, sorry here, it's a bracket missing, all the time smaller than 1, and bang-bang, which means that the norm in L2 in space in O of U of t is constantly equal to 1. So how can I, of course, the way I want to present this is an application of the previous theorem. But I have to check the assumption, which is not so easy. Not so difficult either, it depends on the assumption. Admissibility is obvious. Bounded control operator, L infinity exact controllability anytime. L infinity is here follows from L2. And L2 has been done by Jafar, Lebeau, and others, under the assumptions I have written. What is less obvious is approximate controllability with control supported in any set of positive measure. This has not been studied previously, or apparently it has not been studied previously. So by duality, I have to show that if I have a solution of my homogeneous equation, which vanishes on the boundary and which vanishes in O 4 times in a set of positive measure, then the solution is 0. How do I do that? I take an orthonormal basis of eigenvectors of the Dirichlet Laplacian with corresponding values lambda n, and of course my solution writes in the usual Fourier series form, where an is the inner product of the initial data with phi n. And so what do you know? If we take the inner product with any function v in L2 of O, I have that this scalar function vanishes for t in E. That's what we know. Now my lambda n's are all positive. I have the Schrödinger equation. Here I use this in a quite important way. Then this means that I can extend this function to a function which is holomorphic in the upper plane. Holomorphic and bounded, because the sequence an will be in small L1. Oh, the sequence an is small L1 because of that. No, the sequence an times phi nv, the coefficient here, will all be in L1, small L1. And so I have a function which is bounded in the upper plane, holomorphic, and which vanishes on a set of positive measure of the real axis. Then there is a theorem for that. It's a theorem of Privalov, which I learned and in fact there are many. Privalov theorem is even much stronger. It says exactly this: that if a function has non-tangential traces on the boundary, holomorphic, and it vanishes in a set of positive measure of the boundary, then it is identically 0. So this is Privalov, which is not an easy theorem. Then I get that z of z vanishes for every t, so I pass from t in E to every t, and x still in O. But now I'm done, because if a solution of the Schrödinger equation vanishes in an open subset O, then it is identically 0 because I have observability. So that's the proof of this result. Now, for Schrödinger equation, we have many open questions. First, what about constraints in space-time? I wrote in 1D. If I put constraints like this, I don't know what happens. Admissibility, of course, will be still obvious. What is not obvious is L infinity exact controllability in any time. L infinity exact controllability in any time would be equivalent to this inequality. Here, remark, I don't have the square. With a square, my inequality would be obvious. I know it. So do I have it without the square? For this and the following question, the complex analysts which I have asked seem to be very pessimistic, seem to say that it's not true. But I don't have a formal proof of that. So this is replacing the constraint by a more realistic one, and the other one is the boundary control, no? Which is very, very natural. I control at what end? So again, admissibility is okay, but where things block immediately is what about the L infinity exact observability, controllability, which is equivalent to this observability inequality. So here, this is, seems to be connected with a question studied by Littlewood in a very different context, who obtained for this quantity lower bounds, which are much smaller than this one. This doesn't mean that this one doesn't work, but the lower bounds obtained by very serious people are smaller. So this, for this also, especially for this, my colleagues, complex analysts, are quite pessimistic. Now, what happens, as I already showed, it's more or less standard to pass from Schrödinger to Kirchhoff or Euler-Bernoulli with these boundary conditions. Z on the boundary is equal to Laplacian Z of the boundary is equal to 0. So you see, the bang-bang property for this problem was formulated as an open question in my paper with Loyac from 2013. Why didn't we know to do it? It's because the key point you will see is approximate controllability from measurable sets. When I prove this for Schrödinger, I use in an essential manner that my eigenvalues were I lambda n with lambda n all positive. Here will not be the case, will be plus or minus I lambda n with lambda n the same. So the argument does not directly work. So I could say if I would that it was such a difficult problem that it required 10 years to be solved, but I think that we were the only one to think on it and not all the time. So one has to make this very relative. So the idea is that, so I denote by A0 the Dirichlet Laplacian with all its extensions possible to this, as I have shown in my previous presentation. So I denote psi is equal to W, so psi is equal to W dot, and I define, so the idea is to use the fact that my plate equation will write d over dt minus A0 over W dot plus A0 W is equal to 0. My plate equation writes like that. I use this factorization again here to use the factorization with A0 boundary conditions are essential. And then I denote what I'm doing is to say, okay, if W is 0 almost everywhere in time, so is W dot. You have a small measure theoretic argument. And so is A0W because when I'm regular enough, it's a local operator. That's important. And then I denote, so I introduce, so maybe I should change the signs here, it doesn't matter. I call this gamma. And I know now that gamma is 0 almost everywhere in time, and for x, you know. And moreover, I clearly see that it satisfies this equation. And now I apply my unique continuation result for Schrödinger, roughly speaking. Then I get that gamma is equal to 0, and I adapt again the Privalov theorem-based procedure, and then I get that gamma is equal to 0. So the only thing is that we need to the problem is that these objects are not so regular. This gamma is not so regular because I have to prove this at a level of regularity, which is that of L2 solutions for W. So W dot minus A0 of C, for instance, this is much regular already, and then when I do gamma dot plus IA0 gamma, I go very far in my extrapolation spaces, but we can write this properly, and also use a result which is quite nice, and which is not really studied used in the literature. It's the first time I'm using it. In fact, it's that, okay, I have z dot is equal to az, and I just know that C z of t, if with z of 0 is in the domain, for z of 0 in the domain, I know that if C z of t is equal to 0, implies z of 0 is equal to 0, or z is equal to 0. So I have observability, but only for initial data in the domain. Does this imply that AC approximately observable? It looks trivial, and many people don't even ask themselves this question. If they have obtained what I'm writing here, they say that the system is exactly observable, approximately observable, which is not, strictly speaking, true. So in fact, here, even we have to be a bit careful. If I know this holds in time tau, here I need to add an epsilon, strictly speaking. So there is a small proof of that, which appears inside, because I have here a kind of approximate observability. Of course, due to the very weak character of my solutions, the approximate observability, when I define correctly the output, will hold only for smooth data. So here, d of A can be replaced by d of A infinity, intersection of all d of A n. So the question is, I know that I have approximate observability for smooth data, then I have it for data in the state space, provided that I add an epsilon to the observability time. Here is not a problem because my observability time is arbitrarily small. So that's the proof. 4 plates, many questions are opened. Claim boundary condition, even in the rare situations where we have information about controllability, we don't know anything about time optimal control. And this is not a very easy, I think, open question. Boundary control, like for Schrödinger, it's open, but and the constraint in both on u of t and x is also an important issue. But here, of course, we should probably first understand the case of Schrödinger before going far. So this is all what I wanted to say about the exactly controllable case. Now I'll go to the parabolic case, or to the null. In fact, I call it null controllable case. In the application, it will be to parabolic equations. So what happens here is that this B infinity of tau, everything can still be defined. Of course, this is the reachable state by L infinity controls will be very small. As you see, the reachable space, even with L2 control for a heat equation, is a very small space with respect to the state space X. It's far of has a non-empty interior. In particular, this is what's annoying. So I will not have a maximum principle, or at least a maximum principle which can be exploited is unavailable. I have some ideas on how to obtain a good maximum principle, but this is not done. So this is why the main tool is a theorem which is derived from the paper. It's a slight generalization of the result of Meitzel and Zeiman from 1997, which says assume that AB is L infinity null controllable from every set of positive measure. So here, it is assumed that either I assume that I put here only tau and I keep an arbitrary u, or I say that u is equal to L2 of gamma, some gamma, I don't know what it is with gamma, and then I can write the constraint in gamma times 0 tau, the constraint. I'm taking sets of positive measure in this product space. So if Z0 and Z1 are accessible, the time optimal control has a unique solution, which is bang-bang. So here the strong assumption is L infinity null controllability from any set of positive measure. This replaces what I had in the time reversible case, which was exact controllability plus approximate controllability from sets of positive measure. And then we have the bang-bang property. The proof is quite easy when we understand the principle. Suppose that, so first we have to prove existence. There is some compactness arguments which work without difficulties. So it's not it's quite standard, I would say. Then for the bang-bang property, let us assume that the optimal control is smaller than 1 minus epsilon for xt in a set of positive measure. Then what I do is that I can construct a control and shift it correctly, which steers my system to rest, and it is active only on E. And then if I choose correctly the parameters and I shift my control V in time as I have to, then I can perturb my control U star by this new control V, and I obtain the control which does the job in a shorter time. So that's essentially the proof, which is detailed in my work with Miku, for instance, but which is essentially the proof of Meitzel and Zeidman. So, sorry? Z0 and Z1, in fact, here this is not necessary with what I said, but no, it is necessary in order to say that I have a solution, no? That I can go from Z0 to Z1. Because I can also say replace this by saying assume that I can go from Z0 to Z1. I can make this as an assumption. But here I take, if it is so, how will things happen? If the reachable space from X does not depend on Z0. That's something which is obvious if I have null controllability. Does not depend on time, and in fact does not depend on zero. But it depends on time if I add constraints, which is the case. But still will not depend on Z0. So here, if I'm in R infinity, I can prove, this is a part of the proof, in fact, which I didn't mention here, that we can go from Z0 to Z1 in time long enough with a control which is restricted. So, because here what I'm saying, I can just go from Z0 to Z1 with a control of norm L infinity, which is of class L infinity. But then I can restrict its norm, and still I can do it, provided that I wait long enough. See, something is missing at the end of this, I see now. Okay. A first example of application of this theorem. So what's difficult to apply this theorem is not difficult. What's difficult is how to check the assumptions, especially this null controllability by L infinity inputs in PDE applications. That's far of being easy. So already in 1D, this is a case studied by Meitzel and Zeidman. Dirichlet boundary control for a heat equation on the interval 0 pi. Admissibility, obvious, we already studied it. L infinity control from the measurable set is equivalent to inequality 5. Again, we know this inequality very well with square here. Even that one is not so easy to prove. And question, does it still hold with the L1 norm here? Sorry? On the left-hand side, on the integral? Yes. Ah, yes, you are. No. Ah, yes, it's E. It's E here. Thank you very much. Here it should be E, not all the interval 0 tau. Thank you. So, and in fact, probably that Meitzer and Zeidman knew this abstract result for a certain time, but they had no example of application, no significant example. And in fact, at the same time, there were several papers of very famous numerical analysts or analysts in general, Borwein and Erdely, which provided the tools for that. So in fact, here the tools appeared at the same time with the application. So it's connected to the famous theorem of Münz from the theory of Dirichlet series. And so what does the result say? It's on polynomials, okay, not on functions in this span, where a new k is k theta with theta larger than 1. So in our application, theta will be 2. And what they have shown is that you can bound this kind of polynomial on 0 row by some constant, which depends what is epsilon here. So epsilon is something lying between 0 and 1 minus rho, but some constant, so depending, roughly speaking, on rho, times the upper bound on a set of positive measure. On the other side of the interval. So this is one of the tools, and so this should be connected to the theorem of Münz, which says that this space is a proper subspace of L2 if and only if the sum of 1 over nu k is infinite. And it has been, this kind of problem has been also studied, but without the appearance of set of positive measure in the thesis of, not in the, maybe it was a thesis of Laurent Schwartz, which has a very beautiful book, gave a beautiful book, Leçons sur les sommes d'exponentielles. And some of these ingredients are borrowed from here, but for instance, the fact that measuring a function on 0, 1 from this space on 0, 1, it's more or less the same as measuring on rho 1. So the restriction application is invertible, but what was missing for our application was an estimate of the constant of the norm. And this has been done by combining some results obtained by Miller, Tenenbaum, and myself, and we have obtained a bound of the norm of the inverse of the restriction operator. And very funny, this was very much connected to the estimates on the control cost in small time for the control of the heat equation. And then there is also some, so passing to these measurable sets requires a passage by the theory of Chebyshev polynomials. This is in the papers of Erdely and Borwein, a major ingredient. And combining all that, but I will give some ideas of the proof, we obtain the inequality. We obtain the inequality, the correct one, which I come here, which is this one, but with E instead of 0 tau. Okay? And these constants will depend only on E, of course, not on tau. So now let us go to our very second example. This one. I situate myself in a rectangle, and I'm controlling the temperature on an arbitrarily small part of the boundary. And I want to see that if my controls of time optimal control exist and if they are bang-bang. Mathematically, for that problem, the equations, you have seen them. For every Z0 in H-1, this is the natural state space, and Z1 in R infinity. I would like to know it more precisely, but I don't know it. This is what it is, this R infinity. But it is a Banach space. There exists a unique solution U star of the time optimal control problem. And this solution has a bang-bang property with U star of T and X is equal to 1 for almost every couple Tx. So here I have the correct, let's say, way of having a bang-bang, because having a bang-bang, which is in L2 norm in X, almost for every time equal to 1, is maybe not so interesting. It means that I have temperatures locally are very high. So L2 norm of the temperature is not really a relevant object. Is not even in the energy, contrary of what many times when we look to the heat equation, we write the L2 norm of the temperature in the energy. This is not the physical energy. The physical energy is the L1 norm of the temperature. But nevertheless, of course, in mathematics, you can work with it. So let me explain the principle. So here it's my operator will be the Dirichlet Laplacian, which is negative, self-adjoint. It is diagonal with an orthonormal basis of eigenvectors phi k and the corresponding family of eigenvalues minus lambda k. With these lambda k's which are positive and go to infinity, so it's the usual picture, which I can formulate in an abstract manner, but which lets us think that it is the Laplacian here, not to mix up things. And now, a space which plays an important role when we do control of the heat equation is the space of low frequencies. So I take a gamma smaller than 1. Luckily, I can take this for every positive gamma, but the gammas which will be of interest will be smaller than 1. And I define a space of, given eta, I define a space of low frequencies, which is the span of all the eigen vectors phi k corresponding to eigenvalues having the property that lambda k power gamma is smaller than eta. And I introduce the orthogonal projecture of the state space X, here it will be H minus 1, onto this V eta gamma. And then we have a version of the Lebon-Robiano strategy, which says that if I'm able to prove inequality 7, let us look to it. It looks complicated here. So inequality 7, phi will be in this low frequency space. Here is my observation in L1. Here I multiply the characteristic function of E prime. E prime, you can think it's E because I'm just changing the sense of time. This is just technical, so you can imagine that it's an arbitrary set of positive measure, okay? Arbitrary set of positive measure in space-time. And this is my observation restricted to an arbitrary set of positive measure. So if this observation dominates the final state, with this is important, with an observability constant which depends on the frequency eta, on the maximal frequency eta. See, here I have another term because I have this. I have to take care of this measure. Okay? a positive measure. Normally in the Lebolo-Barnard strategy, you have only this part, d0 exponential of t1 eta. And also, you don't have, it's written for eigenfunctions, for eigenvectors, which is not convenient for boundary control problems. If you want to apply directly to boundary control problems, you need to formulate it already for the semigroup. So this is it is a final state observability estimate, but a weaker one than what we would like to. What we would like to, in fact, is to have this with a universal constant. That's what we will get at the end. But here, first, we have it for phi only in the space v eta gamma, and the observability constant depends on eta. But the conclusion is that, in fact, we can get rid of these ones. We can put at the place a universal constant, and it will be true for every phi. So it's a strange, a kind of strange formulation. I assume that I have a quite weak observability inequality, and I obtain that I have a much stronger one. Over E. So this is why it's a version. We had to take care of this E. So this is a proof, as many of my proofs, really by hand. So we develop as a Fourier series, and we take the trace on gamma. Then, so doing this, I translate my inequality. My inequality, I translate it in terms of a Fourier series, and that's what I obtain. So for the moment, I did nothing. I just rewrote the inequality in terms of Fourier series. Because here my observation, it's my solution is sum of a and m exponential of minus m2 plus n2 sigma sine nx sine ny, but I derivated and I took y equal to 0. This is why I have only sine nx. But still my sum is in m and n, but not in all n and n, only those inside a certain disk of radius eta. Okay, so I have now some technical assumptions connected to this positive measure set stuff. And now, so in fact, I will see that my problem is that I would need an inequality, a lower bound for the sinus, for combinations of sines and nx. I would need this, but when I measure only on a very small interval, so not on 0 pi, because on 0 pi is very easy. And I need also a bound for the sum of, where do I have the, it's missing the exponential in time. It's a bit strange. I think that an exponential in time misses here, and I need something of the type of the results of Zeidman and Meitzel for the exponential in time. I'll make this explicit immediately. So how do I handle the lower bound for the sums of sinus of nx? This, in fact, would be this inequality. So I am in 2D, but when I restricted myself to the boundary, I am in 1D. So I have an inequality of Nazarov from 1993, which says that if you take a trigonometric polynomial like this, here nu k can be anything because they are just different, because I have a finite number of them. Then if I measure on a set of positive measure E, I retrieve the supremum of this trigonometric polynomial on all the interval with a constant which blows up when capital N goes to infinity. So it's exactly, in fact, if we think better, imagine that E is an open set, it is the Lebor-Robiano spectral inequality in dimension 1. But in fact, in the case when E is an interval, an open set, the result is even older, 1948, and is due to Turan, so a number theorist. So strictly speaking, the Lebor-Robiano inequality in dimension 1 is not a trivial result, and it has been obtained by elementary means by Turan. Going to measurable sets, Nazarov is already very complicated. This is why I'm so admiring, we'll see at the end, of the fact that this result has been generalized in several space dimensions very recently for, instead of exponentials, the eigenvectors of the Laplacian. So really you see that here is a huge advance because already Nazarov is a very delicate result. And then, so here I mentioned Turan and the constant. So we handle the, let's say, the lower bound for the space variable in this way. And for the time variable, it's more or less like in the 1D case, but we have to work on that. So this is how things are done for this very simple example. So we were in a rectangle. Now what in an arbitrary geometry? Here I will take B to be bounded, so my control will be, I have heat equation with a distributed control inside. And then I really can think to the Lebor-Robiano inequality, which says that if phi lies in this space V eta gamma, from some gamma smaller than 1, in their case it will be 1/2 for the heat equation, then I have this inequality. So what does it say? It says here I'm observing only combinations of eigenvectors. It says that these combinations are observable, there is no time. But with a constant which depends on the highest frequency. From this, it's a simple, standard by now functional analytic argument, which tells that you have null controllability, and even people, including myself, have been working on how to get the control cost from the constants D0 and D1 in an optimal way. Okay, and then big advances in these directions were in a series of papers of Escauriaza, Wang, and co-authors, which have shown using propagation of smallness properties, results of the type free circle Adamar theorems, and also some Carleman estimates. They have shown that this inequality, which has been shown to hold by Lebor-Robiano for O open set, still hold if O is a set of positive measure. And then things go more or less just by functional analytic approach, and we obtain the result. So this is, however, complicated papers already. And recently we have some important advances, namely if we want to look to variable coefficients. So in my previous talks I was saying it is essentially open, but there is a paper of recent work of Burke and Moyano, where they use very, very deep results of Logvinenko and Malinikova, and using this, the impression is that things become easy, but it's just an impression. And they are able to prove that this holds, so the spectral inequality, which I'm missing, it's here somewhere, here, holds when my operator is the Laplace-Beltrami, the Beltrami Laplacian on a manifold with or without first and then with boundary. In other words, and moreover, the observation set can be even smaller than a set of positive measure. I don't know any application of that now, so they obtain the inequality for sets of a certain Hausdorff measure, which is positive. So this is even smaller sets, but very strange. Maybe one day we'll find an application also to that, because to be honest, I would never think that I can find applications to controls in a set of positive measure, which is not an interval or an open set, but here they are. This is something which is done. Then what about system in general, and in particular Stokes? For Stokes, it's a good hope to do things, because there is a paper of Lebeau and Chavez Silva, where they prove a spectral inequality for the Stokes operator. And so in an open set. Now the question is, can we adapt this to the sets of positive measure? It looks very likely due to the elliptic character of the operator, but of course the Stokes operator has its particularities, a kind of non-local character, and so it has to be studied. And finally, if once problems like Stokes are understood, why not Navier-Stokes? Based on the fact that for some nonlinear system like viscous burgers, there are works of Kunish, Wang, and co-workers, which do interesting results in this direction, certainly sometimes by relaxing some of the constraints, because it's in a nonlinear setting, but in a certain way combining a possible good spectral inequality for Stokes with the nonlinear techniques of Kunish and Wang, it looks likely that one can obtain significant results for Navier-Stokes. So I was too quick today. We have more time for questions.
So I asked the audience if they have questions on the online also, so they can unmute and ask Professor Tucsnak the questions.
Yes, thank you very much for the talk. So I have some question. Perhaps it's quite technical, but okay, it's just for the beginning of the talk. Sorry, it's for the Schrödinger equation. I have not really understood why you assume that you control with some open set satisfying the geometric control condition. Because in the rectangle, we know that
I said that either it's a rectangle, yes, with any control region, or
okay, sorry,
or it's any set with geometric optics. So okay. I took two cases in which I know
yes,
true.
Sorry,
they are not the only ones, but
okay. And I have
I do.
Okay. Yes, a technical question on a slide. It's when you are trying to apply Z-man strategy or for the heat equation. So if
I should, but yes.
I will tell you.
Yes, because I take the initial data to be Z star of delta with delta small, and so I play, and my initial data is 0. So I play with delta.
Okay. Thank you. So yes, another question that I have is, yes, no, it's just a comment on the, at the end of the talk, you said that for the Stokes equation, we don't know that spectral estimates holds for
measurable
set of positive measure, but actually it has been done recently by Chavez Silva, Souza, and Zhang.
And Kanzang?
Yes, and Kanzang.
Maybe even I saw it, but I forgot. Yeah, thank you, yeah. Thank you. Yes. So if it is not bang, then it will be, it needs to be smaller than 1 in absolute value. If it is not always 1, it will be smaller than 1 minus epsilon somewhere on a set of positive measure. And this is why I get a contradiction. Assuming this, I get a contradiction. The contradiction being that I can construct another control, assuming this about U star, which I suppose optimal. I construct another control which will be U, which drives my system to 0 quicker. So I'm not sure I understood, sorry. Yeah. So the minimization here is very particular. The cost is the time. Yes, no, it's a bit, no. What we are saying that the minimal time control is bang. Then how we compute the minimal time control? This doesn't give me the minimal time control. Then to compute it, this information that I know that is bang can be useful. I don't say it's always useful because if I am between 1 and -1, for instance, I have here U and here T. So I need to be between these two lines. What the bang tells me that the optimal control will be either 1 or -1. So it will jump from 1 to -1. And then to compute it, this information is useful to compute it because somehow the problem is reduced to knowing where it jumps. But only when I know that, but this I have to do it differently. Only when I know that, I can compute it. So the way it goes is like this. If it's optimal control, it is bang, and bang reduces the problem to computing where it jumps. The problem is that it can jump very quickly. And that's another question which is asked usually. How many times does it jump? Because if it jumps 10 million times, it will be difficult to compute. We don't really know. For parabolic problems, for special final and initial data, we can have an upper bound of the number of switching. So now if you know if it doesn't switch more than 100 times, you can do it. You can do it, yes. But in the case where the eigenvalues are purely imaginary, like Schrödinger, even if we project on a finite dimensional space, we may have an arbitrary large number of switches. So computationally, it's very difficult. I don't know how people really do in the skew adjoint case. But in fact, I know. So in practice, what engineers add to our problem is that they say the switching time cannot be smaller than a certain quantity. And then they found a solution which is maybe suboptimal, but which is realistic for application. Yeah. No. I'm not looking, but it turns up, but that's how they are in many situations. I'm not looking for them from the beginning, like this. Yes, it can appear also in other control optimal. For example, when you do norm optimal control problems, also appears. But I'm not imposing from the beginning that they are bang. This exists also in people which do that, but that's another question. Yes. It is Pontriaghi maximum principle. It's a particular case of Pontriaghi maximum principle. Yes.
So is there any other questions? Okay. If not, well, thanks, Professor Marius Tucsnak, for the wonderful lecture series.
And thank you. Thank you so much.